Jæja, ég held við byrjum bara. Takk fyrir komuna á málstofu Hafrannsóknastofnunar. Þó að standi reyndar hana innanhúsfræðsla, þá þetta málstofa. Við erum nefnilega frekar heppin í dag að fá gest hingað til okkar. Hann Lars Henrik Smedsrud, sem prófessor við Háskólann í Bergen, og hann ætlar að tala um hita og seltuhringrásina í Norður Atlantshafi, eða AMOC. En erindið hans eru vísbendingar að hita og seltuhringrásin í Norður Atlantshafi sé að veikjast. So it will be in English, obviously. We are very happy for you to be here. Very excited. The floor is yours. Yeah, one reminder, this is being recorded. There will be questions in the end, and if you have questions online, just use the hand option at Teams. Thank you.
So thank you very much for inviting me. It's nice to be here in Iceland. I will be here for a week and have the opportunity to see more of the island as well. So yeah, it's so easy for Norwegians to fly across here now, and I guess I know Theo best here. I was had the pleasure of being his supervisor when he worked on the Fram Strait freshwater export up in between Svalbard and Greenland up here for his PhD. So that's great, and I thought I would actually pose a small question to the audience to start with, because I don't know how much you know about the circulation here. So this is a nice way of looking at the ocean currents that we will discuss today. The backdrop temperature, the color is temperature, so you can just click on this map, right? So the temperature in Bergen is now, outside of Bergen, is now 12 degrees, and outside here in Reykjavik, it's is it 9? I'll get my glasses. Oh, that's, how did that happen?
Just click on the map again.
Yeah, and then, you know, so what is seen here is that, yeah, so obviously what we see on the, wow, you need to help this, is it advertisements? Okay, so, but I can point, I thought. This one, yeah. So on what happens here is that you have the warm Atlantic inflow, and the animated colors, or the stripes, are the best shot at the flow today, right? So you see that there's inflow along the coast of Norway up to Svalbard, and then you have a Barents branch branching in, following the coast of Norway, and then you have the cold, fresh water flowing down from the North Pole, where Theo did his PhD work. So there's a bit of sea ice coming down and fresh water, and that stays more or less along the coast of Greenland all the way down here to Iceland. So that's, and then I thought, is there, do you know what the AMOC is? Are you all familiar with this term? You're nodding. So if I ask the blonde woman in blue shirt, can you explain AMOC just in two sentences? What would you say it is?
It's the ocean currents coming from the US, sort of, or from the Atlantic Ocean.
Yeah, like what we're seeing here. Yeah. But yeah, so it is. That's true. But then it's so. But then. Yeah, Theo, can you, what's more than the currents? So it's a special type of currents, right?
So, I mean, I would say that it is the meridional, which means from north to south, north to south. Yeah. Overturning means from up, to bottom.
Yeah.
Circulation, which is in the Atlantic Ocean. So basically, it is not wind-driven. It is driven by something else. This has pressure differences.
Oh yeah. We don't hear him. Yeah. Okay. Yeah. Okay. So he's yeah. So okay. Yeah.
But yeah, overall it is, as Egil said, warm water that comes through the water column from the south to the north, warming the Nordic countries.
Yeah. So, but importantly, it's so all of the currents you see here are the currents in the surface, right? So the AMOC part of it is the flow going north in the surface, and then the dense cold water returning along the bottom southwards. So the main point I think that will be important is that, so if you have strong inflow here along the Norwegian coast, which is warm, and you have fresh water flowing out here along the coast of Greenland, which is cold in the surface, the AMOC will be 0. Right? So the AMOC is only the part that's flowing north in the surface, getting denser and returning south. So regardless of what will happen to the AMOC, there is today and there will be always in the future, as long as the Earth is turning and there's extra sun and the tropics and it's cold at the north, there will be a horizontal flow, which is quite strong. And you see it here, right? So there's strong inflow and you add fresh water in the north, and this returns south again. So if the AMOC, magically could stop, it would still be a large horizontal flow, which is important also for bringing heat towards Iceland. And I think and this horizontal flow that you see here is in very large parts wind-driven, and will be wind-driven if there's wind in the future, and there will be wind in the future. So that's going to be my main point, I think, and then I can start my regular point. So so now we know a little bit about why there's currents. There's currents due to wind, and there's currents also because you're cooling and the water gets denser and it flows south. So I've assembled my best shot at what you would like to know about this system from a bunch of researchers here in Bergen. So all of these people have contributed to what I'm going to say now. And we all work at this Bjørknes Center. So some people work in, I think, what is comparable to this institution at IMR, right? So that's Øystein Skagseth and Til Baumann, and the rest of us works at the university, which is all part of the Bjørknes Center. And a little bit about me. So I'm a normal professor teaching most of my time in Bergen. I did my PhD up on Svalbard, looking at some small ice crystals, which are called frazzle ice crystals. And then I've been to Antarctica at least once, twice. Yeah. And then I also had a position at UNIS, so quite enjoyable. I think we take students out into the fjords of Svalbard, and then we use the the governor on Svalbard, a vessel called Polarskyssel, and take the students out, and then we measure, for example, atmospheric temperatures and turbulence in this mast here. So I've done a bit of different things, and then I'm going to support my views now with a very nice organization called the European Academy Science Advisory Council. So I understand that this institute, you provide also advice to politicians, and this organization then is trying to do this at an European level. So there's a number of reports which are written by selected people from these academies, and then they are approved by all these European academies, right? So it's like it's the scientific Olympic gathering of Europe in a way. And I'm a part of this environmental panel now, and I just thought I'd point you to some of these reports now initially. But just to be clear, I do worry about global warming. So this is maybe a little bit personal, but I'd say that we have a large problem with burning fossil fuel, and we really need to stop. I'll say there will be large problems with melting ice, sea level rise, ocean acidification. I'll say that there's going to be large areas like Spain where it's going to be too dry. It's going to be really difficult to find the water. There'll be lots of forest fires, So generally the problem is that the world is getting too warm, and I'm also quite worried about ecosystem collapse. And I think we all, scientists, we really have a responsibility for telling politicians what we worry about. But then, when it comes to this collapse of AMOC and large cooling in Iceland or the Nordics, then my strong view is that this is not going to happen. And I guess the rest of this talk will be about why I think so. So if you would like to read more on it, there is this nice report from the EASAC then. So it was called A Sea of Change, Europe's Future in the Atlantic Realm. was published in 2021, and I was one of the co-authors there. And you know, my views today, I think, are consistent with what we found then. There has been, I mean, I'll show you some new observations, but it's consistent with that, right? And another really interesting report now, I think, is this one, you know, changing wildfires. I don't think you have this problem in Iceland, but in Theo's home country like Greece, I think, you know, so this is a major problem with global warming. And so I do worry, but not about the AMOC. So I'll tell you why. And so the EASAC produces a lot of interesting reports. So these two I've already mentioned, but there's a, you know, for example, there's a really nice one on decarbonization of transport. And I think, you know, the number one take-home message there is that, you know, I mean, you just need to transport less. If you have an electrical car, it's kind of okay, but you still, your tires still produce plastic, right? Rubber, microplastic, and you still use a lot of energy. You still need a lot of metal. So the best way is, you know, to get to work is catching a bus or biking. And there's a report on just, you know, that there's really too little happening when it comes to policy, right? So the climate is deteriorating. There's huge economic loss because of climate change. There's a lot of resources being wasted, and we are risking, you know, the biodiversity. So there's a lot of things to worry about, but not the AMOC in my view. Okay, so then these days we can go to artificial intelligence, right? There's a very nice one called Consensus, if you haven't seen it yet, and you can pose questions, and when you pose a question, you get the answers just based on scientific journals, right? So it avoids all the noise in the internet, just uses scientific journals. And here I made sure to pose a question where I got roughly 50-50. So this, I think, reflects the science community these days. You know, so will thermohaline circulation in the ocean slow over the next century? So by thermohaline circulation, we mean the AMOC, right? It's how the water gets denser and sinks down and returns south. So here you see that there is, you know, half the paper says that it will slow down, and half the papers say it won't slow down. And I think that reflects reality. So it is quite likely that it will slow down. It's, you know, it may not slow down, but you know, I did not say collapse, right? And then I hope I would get, you know, a very different distribution. But there, you know, it will probably slow down somewhat, and this, yeah. So that's why there's so much writings about it. I think, you know, that. And it's complicated, you know, in some ways, and it's difficult to understand, and then journalists get it wrong. So I think that's why it ends up doing like this. So a part of what and then you get a nice explanation with the citations if you do this, right? So it says that, you know, model projections says, you know, that the AMOC will weaken. I think that's correct. There's recent observations, very few, there's almost no trends. And I'll show you that. Their models disagree. So some models, they reduce this circulation a lot. Some models reduce it less. And so there's differences in what it happens in the future. And then, you know, there's consensus that if we get too strong warming, then, you know, there'll be more melting of Greenland, and then, you know, worse things can happen. So I think 98% of scientists agree that we should prevent global warming as much as we can, right? But then it's the, you know, the reasons why we should do it that we disagree on, maybe. So my own contribution here has a nice cartoon like this. So this came out 3 years ago now, then, but I did this review of the Nordic seas and heat loss and Atlantic inflow, and also a bit of sea ice cover. And it's always nice for a Norwegian to be able to cite Fridtjof Nansen. So already he noted back in 1902 that Atlantic water is the key heat source for the Arctic Ocean. And by the Atlantic Ocean, I agree with. I saw on the Icelandic air flight coming here yesterday. It has the name Arctic Ocean, just north of Iceland. So I fully agree. I mean, the Arctic, in my view, starts here in Iceland and it goes all the way to the Bering Strait. So sometimes people think about the Arctic starting at Svalbard, and I think, you know, the Nordic Seas So and oceanographically, you see it here, right? So Iceland is in this cartoon here. It's a quite shallow strait between Greenland and Iceland, and then it's also a ridge going from Iceland to Scotland, and then north of this ridge there's a really deep basin, right? So you have the Fram Strait here, but it's quite deep, and you have the Lomonosov Ridge, which is I think 1,500 meters. But you know, so really all of this is one basin in oceanography. And this review, and then what we'll talk about today is then, you know, how much Atlantic water comes in, and then to some degree how much it's cooling, and then the ice edge is moving dependent on how much water is coming in, and then all of this water of course needs to leave as well. So a lot of it leaves as the dense water and this overturning. So this overturning is sketched here as the blue arrow, but then there's also fresh water exiting here along Greenland. Is it possible to see this? Okay, there's the laser pointer. Yeah. So there's, you know, this was the fresh water, cold fresh water we saw in the animation to start with. And this, so what happens notably in the Arctic Ocean is that this Atlantic water, it meets the ice edge, but then it carries on. So if you take a temperature salinity profile at the North Pole, you'll see that the upper maybe 100 meter is very fresh and cold, but deeper down you'll find Atlantic water, and it spreads all the way across to the Bering Strait. So you know, Atlantic water is found everywhere in the Arctic Ocean. Okay, and this is the system we're trying to understand then. So overall, I don't know if you work a lot with the unit Sverdrups. It's a lot of water. It's 1 million cubic meters per second, and it's close to 10 flowing in, and it flows in mostly between Norway and Iceland, but there's actually a small current also following the coast here. So it's like one Sverdrup coming in on this side of Iceland, which is not in the drawing, but then it flows north, and then almost everything returns south across this Greenland-Scotland ridge that Iceland is in the middle of. And then you have a little bit of a fresh outflow here in the Davis Strait. So, and then you note maybe that the Bering Strait is very, very shallow. So less than, you know, it's a 90% of the water that flows into this Arctic Ocean happens here, and only 10% on the Bering side. So that's important. And then not so long ago, I mean, so I think one of the best time series of the inflow is the one done by people at my institute, and it's called Svinøy section, and it's here off the coast of Norway. And, you know, the one good reason for it being a very nice time series is that it's, you know, after all these complicated circulations around the Faroes, around Shetland is finished. So when you measure the flow here, all of that water is already inside the basin. So it has passed Iceland, it has passed the Faroes, and it's well inside the basin. So it has to have arrived inside. If you measure it around Faroes, you might find it that it circulates the island and it's a little bit uncertain. And this is the time series. It's the longest time series we have of currents in the Nordic Seas or the Arctic Ocean, and it goes back to the 1995, and you see it goes up and down. It's significant variability, but there's zero trends, right? So there's a steady Atlantic inflow. And then we can look further south. So I heard this morning that, you know, people have heard that there's some trends. Svinøy section was what I just showed you. This goes back to mid-90s, and this is the smooth variability. And then we can start down here in Florida. That's where the Gulf Stream originates. It's called the Rapid Array. It's between Florida and Bermuda. And so down here, the flow is around about 30 to 34 Sverdrup. So it's a lot more water. And a lot of this water that flows around here goes south, right? So it's only a third of the real Gulf Stream that comes across into our area. And you see that the Oleander section here, you have the Gulf Stream, it gets as big as 100 Sverdrups. That's because there's a lot of water that is circulating in the north, in the subtropical gyre here, and it's wind driven. And then you have this O-snap array, it's very short, but then you see this Greenland-Scotland Ridge inflow. So this is summarizing everything north of Iceland, north of the Faroes, and here around Shetland. And you see it's varying, but there's no trends. So I'll show you. This is kind of the only AMOC sketch I have, but so we now saw that, so there's large horizontal circulation, and the AMOC is only the vertical part of it. So it's what flows north in the surface, gets denser, and returns south. And also, if you calculate this overturning down here at the rapid latitude, so this is 26 north, it's varying, but it's not really any trends. There's a new section here, because they realized that we need to measure it further north. This is also semi-stable. And then up here, it's the same thing here up in the Nordic Seas, that it's, So I said about between 9 and 10 Sverdrups are coming in, and you see it's about, between 5 and 6 of it is the overturning. So 30%, or a little bit dependent on how you calculate it, is, so I'd say roughly 50% of it is flowing in the surface, going down and returning back, and 50% is doing the horizontal gyre. Okay, and then so this is just the time series from Florida, right? So the one I showed here, so the rapid array, and was a new. So there was a small trend, and people were worrying a lot about it until last year, and then so the way they measure the flow in the Florida Strait is that they just have a telephone cable across, and the salinity, the flow itself generates a small magnetic field because the salinity is it's generating a magnetic field. And if earlier they forgot to correct for the Earth magnetic field changes, so the magnetic North Pole moves a little bit. But when they did that, then that trend magically disappeared. So since 2000 until now, the Florida Strait current is also very, very stable. And then the most updated information I have, this is from the colleagues at IMR in Bergen, so your counterparts in Bergen, and they are working on this flow up along the Norwegian coast. And then they look at, so they have these 4 standard sections in Norway, like Svine, Gimsøy, Barents Opening, and then Bear Island up here. So they do these in a similar way as you do, like 3 to 4 times a year. And then you can calculate the currents if you have an ADCP on board your ship. And then also here, they are looking at the sea surface height, so the tilt. And they calculate the currents, and you see it's a lot of up and down, but it's basically not any trends. So it's all the way until today, it's very, very stable. Well, it's varying, but there's no systematic change, which we call trends, right? So, and then flipping back to my long-term view. So when I wrote this review some years ago, we wanted to understand what has happened the last 100 years. Because we know that the Arctic sea ice cover has melted, and we know there has been some changes. And in that simulation, we found that, since consistent with the observations, there has been no or no systematic change since the, say 1990s, but we found a small, significant, stronger Atlantic inflow over the last 100 years. So this can help explain why we have seen a warming of the, so you may have heard about Arctic amplification. So Svalbard, for example, is warming up much more than the rest of the planet. And I think this is part of it, although it's difficult to prove. And I remember I met your very clever author. This is Stein, the guy with the fish has no feet, and what was his name? Very famous Icelandic author. No, the Stein. Yeah, I think so. Well, he was at that.
We have a lot of pain.
Okay. Yeah. But he was married to this TV lady as well, and she was there, and she had just. Von Kalm, yeah. And they said that the Iceland was the only place in the world that got cooler, right? Because they had just come from, if I have time, I'll show you some results on this cold blob, but it's no longer true. So I think yeah, okay. And so if you want to understand how much the Icelandic areas are warming up, I just downloaded this. So this is the average surface ocean temperatures in a large section of the North Atlantic. And here you see, so I think the orange line was last year. That was a really warm year for the North Atlantic. But you see also this year, it has been quite a warm year. So you see the 1980 to 2010 average is here, the dashed and the dotted lines. And we are still on so there's a large seasonal cycle, of course, warmer in the summer and colder in the winter, but we are definitely in a warming era. And this is, I think, what most people think about as the cold blob. So what I'm showing here is just downloaded from this climate reanalyzer map, but this is how the surface temperatures are compared to the 1950 to 2000 average, right? So this year you saw this is 2020, and here you see it's quite warmer here, but there's an area south of Iceland where it's colder than normal. But if you then just flip through, this is 21, 22, 23. So for example, in 23, all the areas around Iceland were about 1 degree to 2 degrees warmer than in the long-term average. And then here along the East Greenland current, it was 3 to 4 degrees warmer. And last year, it's the same. So I'd say that the ocean areas around Iceland are definitely warming, and I think this cold blob was related to some physical change that we can discuss, but whatever it was, it's gone. So what we see along the Norwegian coast is if you care about the last 30 years, it's roughly 1 degree warmer now than what it was. And it's actually a little bit of like an Arctic amplification here. So the Barents Sea, for example, is getting more warm than the Svinøy section and the Gimsøy section, but it's roughly, if you just want to remember a few numbers, 1 degree the last 30 years is reasonable, and this is an updated map then. So the North Atlantic, Greenland Sea, Iceland Sea, and Norwegian Sea is warming throughout. And then I thought that, okay, I'll say something about the sea ice. So you used to have, I think there's like a Storis index, which is how often do you see sea ice on the north coast of Greenland? No, Iceland, sorry. And I think, so in the previous times, you would sometimes see the sea ice edge on the north tip of Iceland. So this is the long-term average here in the black line for March. So this is March, and this is September. So in September, of course, in the end of summer, the sea ice edge is a long way away from Iceland. But in the winter, you used to get sea ice a little bit touching your coast. And then this is the trends over the last 30 years. So I worked a lot in the Barents Sea, and we saw that this exceptional warming of the Atlantic water there has caused the sea ice to retreat. But I think to some extent has also happened here north of Greenland, north of Iceland in the Greenland Sea. And I'll just show one example of that then. So I don't know if, have you heard about the Odden ice tongue? So this was like a feature, and you kind of see it here. So in the 80s, it was a lot of Norwegian sealers that went up there to catch seals. So this is the long-term change of sea ice in the Greenland Sea. So this is the coast of Greenland, and so before 1980, the sea ice used to be roughly out here. So covering, this is the Greenland Sea center, and then there was a lot of years in the 80s and 90s where the Odden appeared. So you had like this special feature, and then after the 90s, you've had the sea ice has retracted here. So it's now more or less sitting along the continental slope of Greenland in the Greenland Sea. And also here, this is just the surface temperature within this area in these periods, right? So we found that it depends a lot on the sea ice cover, and you know, since early 2000s, then we've had this area has not been sea ice covered, and the temperatures are roughly 1 degree warmer than it used to be back in the days when it was sea ice covered. So also here in the Greenland Sea, you see this 1 degree warming. And if you want to understand what has happened, you need to look at sections. So this is a nice paper by another PhD student from Bergen. So this is all the data we could find from the Greenland Sea. So it starts in the 1950s, and all of these stations, the small dots, are observations within this area here. Right, so there's a huge number of observations, and in the last years, you see there's a lot more stations, and that's usually the Argo floats. So that's a nice US contribution to society. So there's, and the temperature here now shows as the colors. So you see from the 1950s until the 1990s, I think, you know, things look quite similar. You see colder temperatures coming up towards the surface here, actually. So there was a cold period at the end of the 70s. We call, back then, some politicians were afraid about like a coming ice age. So we're discussing whether we should try to prevent an ice age coming. And that didn't happen. And now you see the warmer temperatures has really crept down. So all, you know, the Greenland Sea has not only warmed at the surface, but the warm temperatures are now reaching down to 2,000 meters. So this is a real tipping point, in my view. It has fundamentally changed the Greenland Sea, and you know, the reason why you had these cold temperatures all the way to the surface is that you had strong winds in the winter, and these, you know, you don't measure all the time. So on some occasions, that water is brought up and you cool it so much that it flows all the way from the surface and all the way down to the bottom. And then, so we call that bottom-reaching convection, and then you get fresh, you know, so it's only the water that's in contact with the atmosphere that has high oxygen levels, and this is the only way really to get high oxygen levels down to the bottom of the Greenland Sea, and this is no longer happening. So I think, you know, if you're a benthic, what is it, or the benthic animals or benthic biota, or what do you call it if it lives at the bottom? No, that's good enough. Yeah. So I mean, you're still forming intermediate water, right? So, but everything has warmed up. So, this is my last few figures on. So, what has happened, and this is from other colleagues then, but so we can look at this system, and this is now back to the overturning, right? So this is the Greenland Scotland Ridge. Iceland is just hiding at the back here, and this is how much water is overturning in the Arctic. So this is the Nordic Seas, and this is the Fram Strait. So this is a schematic of what it is, and you see this is from some ocean reanalysis, so like weather models, but just for the ocean, and it's forced by observations as well as we can, and you see that it matches the observations well. So what has happened here is that, you know, this reduced cooling of the Greenland Sea and the warming has made this, you know, so it is reducing the dense water formation, right? So everything is warming up, the water is becoming less dense, and therefore it sinks down to a smaller degree within the Nordic seas. So this is somewhat reduced, but on the other side, because the ice edge is moving north, there's more cooling going on in the north. So if you just look at how much dense water you're making north of the Fram Strait or north of the Barents Sea opening, there it is increasing. So some people call this Arctic meridional overturnings, or AMOC. But the main point is that, you know, when the sea ice is retreating, there's larger cooling happening, and this is it's well, depending on what you want to happen, it's a negative or positive feedback. So the system is able to get rid of the heat and create more dense water because the ice is retreating. So I think this is the last part about what has happened, and then there's a few slides on the future. But so, you know, on average, if you just want to care about where is the water getting dense, it's this red color here. So this is, you know, so it comes up along the Norwegian coast, and the reason why it's white there is that we're only looking here at the water that is becoming denser than some density class. So it's it hasn't reached the proper density yet, right? So, but then, you know, it's a lot of cooling in the West Spitsbergen Current west of Svalbard, and it's cooling here as well, and it's also cooling in the Barents Sea. But then if you look at the change, so how this has changed over the 1990 to 2020 period, then you see that there's less dense water happening in the south, but there's more dense water being formed in the north. So the cooling moves north with global warming, and this is the explanation for why we've had a quite constant flow, in my view. So that's it, really. I have two slides also for the future. So I'm not saying that the AMOC is not going to change. I think I'm saying that it has not changed yet, right? So all our observations say things are normal until now. We have released a lot of CO2 into the atmosphere. We will see future warming, and this will, I think, you know, it will slow down, or, you know, it will decrease the AMOC. So this is the best shot we have. This is the present climate models, and in over the next 80 years then, or 75 years, these predict that we will get this, you know, the AMOC will reduce some, you know, actually 50%, so that's quite a lot. The Gulf Stream will reduce 30%, so this is also, you know, significant, and we should worry about it to some degree, but it's not going to collapse, right? It's not going to stop. It will slow down, and it's related to what I showed you about the Greenland Sea, that you're no longer cool, you know, you're not, everything is warming up and it's becoming less dense. But then that does not mean that the heat transport is going to be reduced to the same amount, because we have this important gyre circulation that I pointed to with the animation. So the ocean heat transport is going to go down less. But the main problem is that the world is warming, and this will, so I think maybe here in Greenland you're going to be lucky. So at least this is the last set of IPCC models. You see that the Arctic is warming up a lot, Alaska is warming up a lot, but just around Iceland, it's a small warming, which is related to this slowdown of the AMOC. So I'm not saying that it's not going to change, but I'm saying that it's not going to collapse. And if you're lucky, it's going to lead to a less serious warming of the areas around Iceland. And it's going to lead to a stronger warming in the north, where the ice edge is retreating. So maybe you can still go skiing in the future in Iceland as well. I think that's the conclusions. And I'm done, and I'm happy to take any questions. But I think I showed you then that since the 1990s, we have good observations of the inflow, and there are no trends. There was, on the contrary, at least the Norwegian Earth System model told us that there has been a slow increase in inflow of Atlantic water across the Greenland-Scotland ridge the last 100 years. And then that increase has put more warm water in here and is part of the explanation why the ice edge has retreated north, and the ice is no longer hitting the north coast of Iceland. And this has helped increase the heat loss both in the Barents Sea and in the Greenland Sea. And so for now we have a stable overturning, and it is helped somewhat by this ice loss. And even though we see that the Nordic seas are warming up, and we are only producing intermediate water and not bottom water, it has been, it has kept the overturning stable. And then, a future reduced AMOC means that Iceland will be, it will warm less, but it will still warm. That's my understanding. Okay, thank you.
Thank you very much. Questions? Halldór?
Thank you very much for an enlightening talk. So the conclusions regarding towards the end of the century are very similar to reports that Hlynur and I and several others took part in making 2 years ago, where we took all the CMIP models and we looked at the region around Iceland. And indeed, depending on scenarios, of course, it will warm here, despite there being occasional cooling episodes sort of going around the Iceland, or going around the Atlantic, sorry. But the problem actually seems to be after 2100. If you read this strange IPCC claim that they cannot exclude, how does it go? They cannot exclude that the likelihood of AMOC collapsing before the end of the century cannot be, there's medium confidence if it will not collapse before the end of the century, something like that. It's a very strange comment because it's hard to know exactly what it means. But in general, it seems to say, well, we don't think it will collapse before the end of the century. Just tell you that.
I think that's...
And that is not the problem. The problem is that, at least in my opinion, is that if you look at the few models from the CMIP 6 ensemble that have been continued, you start seeing collapses there, either partial collapses or complete collapses. The big part there is actually because the CMIP is not a sort of probability space, so it's hard to know exactly, people are taking all sorts of odds out of this, saying there's 27% likelihood or something like that. I have no idea if that's correct or not. But it sort of seems to me that if we are trying to do this from a risk analysis perspective, what we should be concerned about is actually what can happen after 2100, and will, in the case of a big collapse there, will we get cooling here, which some of those models show.
Yeah, so I think you're very informed, and so this is still the worst business as usual scenario. So I think we all agree that we should stop we should stop burning fossil fuel, so that we don't end up in the worst case scenario. And then clearly the less CO2 we emit, the less warming we will have, the less Greenland will melt, and the less risk there is for large reduction in overturning. We just had a nice meeting in Bergen where somebody from NCAR, so they're running the Community Earth System model in the US, and they looked at what is the difference between low resolution and high resolution coupled models. And consistent with what I just showed now, they say that, if you run a high resolution model, there's less reduction. So I think, the main conclusion, or the one reason I wanted to show this initially, was it this? Yes. It's a strange browser you have. So I think this is, the scenario with a collapse is that there's so much melting from Greenland that fresh water is getting out from Greenland to this region of for example, the Greenland Sea that I showed you, that you're preventing this, the bottom water formation or the dense water formation. But it's really hard for fresh water to get from the coast and out to the middle of the Greenland Sea. And the higher resolution model you have, the more difficult that is. So a systematic problem with the coarse resolution climate models is that they're too diffuse. So they're spreading this fresh water too much out. So I'm thinking, nature is more resilient than the current global models because of this effect. And there's also this effect with the sea ice that you cool more. This is all happening in the boundary currents, which will be better resolved. So I think nature is more resilient than the models. And some of these people that say we don't know, that's true, but there's no good reason to believe that nature is more unstable than the models. I think there's a lot of good reasons to believe that nature is more stable than the models.
Just while you're on this picture, would you mind explaining the bit about the Greenland deep sea cold water disappearing from a spatial perspective? Because it's hard, for a non-specialist to understand what's going on that side, because it's a completely different than on the between the Faroes and Iceland.
Yeah, so the Greenland Sea gyre is this bit in the middle where there's very little flow. So it's a good place to study year-to-year variability, because there's it's kind of a gyre where water is flowing around and around. So for that reason, I guess you're familiar with the mean surf. Let's see if we go to the winds. So maybe I'll just explain it. Ooh. No, I messed it up. Yeah. I need
I'll rescue you.
That's a strange browser you have. Okay.
Let's not talk about that.
Okay. Yeah, that's fine. So
you want to show something here, or?
Yeah. Well. Yeah. So I mean the average atmospheric circulation in the Nordic seas is that you have a low. All know about the Icelandic low, right? So that's why it rains quite a lot here. So the stronger you blow the winds, so the winds blow like this. So you're Ekman pumping out. So you're pushing this Atlantic water towards the coast of Norway. You're pushing this fresh water towards the coast of Greenland. So you're bringing up water from denser layers and especially so in the Greenland Sea. So that's why. So if you look at the density, the isopycnals, so the lines of constant density, they are doming in the middle of the Greenland Sea. So that's where so all of this water has cooled in the Barents Sea. It's come around the Arctic Ocean proper, comes out the Fram Strait, and then it's being lifted towards the surface. So you bring it back to the surface and you cool it a little bit more, and then it gets really close to the freezing point, and then it becomes super dense, and then it used to go all the way down to the bottom.
And carry the oxygen
with it. Yeah. So yeah. Okay. And that doesn't happen anymore.
Okay.
That's a bad thing if you're a benthic animal.
More questions, and you can also ask online. Yeah, Theo.
So, Lars Henrik, thank you very much for the talk. I mean, it is great to have physical oceanography in this room. This is not so often, so at least I personally am very happy about it.
Oh, thank you.
So, it is not a question, it is a comment. I personally asked you when you told me that you're coming in Iceland to give a talk about your point of view and your understanding of what is happening with the AMOC. And that is because it is something which is, for which people are very interested here. This is my understanding for the time that I have been here. Sometimes it appears as something very dividing between physical oceanographers. So basically, it appears to be sort of a heated debate on what is going to happen. And sometimes this is discouraging, I might say. But so my comment is, it steps on what you said before, and this is something that we need to remember, that nobody disagrees that what we need to do is, as soon as possible, stop emitting carbon dioxide, reduce emissions. There's nobody disagreeing on this. So this is something that we should remember, I think. And then, there are opinions. Unfortunately, science is not like one arrow pointing to one direction. It is different arrows pointing into different directions, and we need to try and interpret the results in the way that we understand best. And then in the end, it's a matter of understanding, if not saying believing. So it is. I agree with you. My point of view on the AMOC, without having studied it, is similar as yours, but this is not important. I think that it is important to have access to both opinions. So basically, be aware that there is a part, what you showed before, 50%, that there is a part of the community that supports that the AMOC might collapse, and this could result into a decrease of temperature, and part of the community disagrees on this. So yeah. It's important to hear all opinions. So that's it. That was my comment.
Yeah, no, I'm worried about what will happen to our oceanographic society. If people get really scared and think that this will, I mean, there was stories in the news in 2023 saying that the AMOC could collapse in 2025, and clearly it has not collapsed yet, right? And I think, collapse is not a word we should use. I mean, we could talk about, so on purpose, I used, reduction, slow down, so it will slow down. And I think, so it's, what the real discussion is about the uncertainty in the models. And the models are never perfect. It's the best tool we have. I think, all the models say it will reduce to some degree. And that's a bad thing if you're a benthic animal. And, it has already happened, in the Greenland Sea. It has happened that we are no longer producing the dense water or the bottom reaching convection. And this is due to global warming. And the sea ice has already retreated a lot. I mean, you'll never get sea ice on the north coast of Greenland because it's getting too warm. So it has a lot of serious effects have already happened because of global warming.
May I ask one question about this slide there? I thought it's cool, but when you pointed it up again, I realized something I wasn't sure about. So it's the 9th of October today, Thursday. Okay, if I say let's meet next Friday, is that tomorrow, the 10th, or the 17th? So the problem here is, what does next century mean? Is it the 21st or the 22nd?
Oh yeah, okay. Well, I take it to be the next 100 years, but maybe,
Yeah, but this is I find this, I've actually missed dates with colleagues in Canada over the question of what does next Friday mean.
Oh, yeah.
I'm not sure exactly, because I probably would have said no there, even though I am very concerned about this, but it's from a risk management perspective mostly. That is, if this goes wrong, then it could have very serious consequences. But I agree that also risk management perspective, it's very easy to fix, stop emitting CO2, because all models seem to show that the less you emit, the less likely this is to happen.
Yeah, so I think we all agree on what we should do and that we worry about global warming. It's just that, there's so many other serious things to worry about. And from what we understand of physical oceanography today, I think we should not worry about an AMOC collapse. And then there are people in Bjørknes Center who also believe that this may happen, that the models are uncertain. And most of those people work with paleoceanography, so they look at the sediment cores and they look at what happened during the last ice age. And then they see some events called danske Ørsker events, where they see that the temperatures around Iceland and in the Labrador Sea, in the Irminger Sea, Greenland Sea, that they suddenly dropped very quickly. I think that is correct. It was then there was sea ice cover there, so there are, but that was the last ice age. There was a big ice sheet in North America. The winds were different. And there was, the sea level was a lot lower down because there was so much ice on land. So there was, it was a fundamentally different situation. And I think you can, so they really know about temperature, but they don't know about flow, because there's very little proxies that will reflect the flow. So all this collapse comes back to a very simple model in oceanography called the Stommel model, where he approximated, the full three-dimensional model or the circulation of the Atlantic into a northern column and a southern column. And if you dump too much fresh water in the north, then that overturning stops. So this is basically what happens in a fjord here in Iceland. You put fresh water inside the fjord, and there's so much fresh water being put that you have circulation from, going south in the surface. So you just switch from this overturning to an estuarine circulation in that model. So the model is correct, but you're not able to put enough fresh water in the North Atlantic. If you dump a lot of fresh water, then your model will respond. But it's a crazy amount of fresh water that they dump in those housing experiments to provoke this cooling. And then Iceland and Norway will cool down, 10 degrees. But it's not, there's not enough fresh water, and it's really hard to get it into the middle of the ocean.
You can actually, in some models, like you just take, there are very few experiments that sort of do this in a way that forecasters like I like, because I use weather forecasting models a lot, and the way you initialize them so that you can actually interpret the results in a probabilistic way is technical, and then you have to really think about what you're doing. Probably one of the nicest such runs is from GISS, NASA GISS, but it's a coarse model, should be said. And there it's clear that you could, even in just a mid-range scenario without any hosing, you can generate partial collapse and even a complete collapse. And the difficulty there is that it's actually stochastic difference that decides which way it goes. So in that model universe, and there are reasons we could have for distrusting that model universe, but in that model universe, you could say things like there's 20% probability of collapse under SSP 245, which would be kind of impressive. But that would not happen. It would not show up in any of your graphs because it happens after 2100.
Yeah.
Thank you. I would like to end this on where you started, talking about advice to politicians. And you all said that we all agree what needs to be done. But if I quote one person here who is quite important in the world today, the quote goes, "It's really cold outside. They're calling it a major freeze, weeks ahead of normal. Man, we could use a big fat dose of global warming." Yeah. So how optimistic are you that the politicians will listen to us?
Yeah, no, it's been a difficult year. I have a Fulbright grant, and I'm one of the reasons I'm here. I'll drive to Akureyri to work with a really clever Icelandic lawyer, Rachel Johnston. She's doing polar law at the University of Akureyri, and we're trying to give advice to the U.S. administration on, Arctic resources. So we picked critical minerals, and we'll go there in April. And we're very concerned, But there's clever people in the administration that are reading papers, and the U.S. still has an Arctic research strategy. So if you read it, it says that it's really important to do physical oceanography, sea ice research, and atmospheric science because it increases our operational awareness, which is what they use that word for the defense, right? And it's important for economic security. So I think I have confidence that science, even a very short-sighted society that wants to increase profit needs research, actually. So that's a positive way of thinking about it.
It's a good way to end it. Thank you very much.